What we're going to do in this video is tackle a challenge that often trips up even the best algebra students, finding the inverse of a piecewise function. We already know that to find an inverse of a function, we generally interchange x and y and solve for y. But what happens when our function has more than one rule? Because a piecewise function consists of different formulas on different parts of its domain, we can't treat it as one ordinary equation. We have to handle it piece by piece, while keeping a very close eye on the original restrictions. Before we even look at an example, we have to bear in mind one important rule. When we find the inverse of a piecewise function, we don't just invert the formulas. We also have to reverse the corresponding intervals or domains of each piece. Let's look at a simple piecewise function together. Here, our function is defined as f of x equals x plus 2 when x is less than 0, and f of x equals x squared when x is greater than or equal to 0. But before we proceed to find the inverse, we need to check whether the function is one-to-one. As we discussed in our previous video, if a function is not one-to-one, its inverse will not be a function. So to check whether this function is one-to-one, let's graph the piecewise function and use the horizontal line test. Here, the first piece is a linear function, y equals x plus 2, which is graphed over the domain negative infinity to 0, as shown here on our Cartesian coordinate plane, since this piece is defined when x is less than 0. The second piece is a quadratic function, y equals x squared, which is graphed over the domain 0 to infinity, as shown here. Now, when we check our function using the horizontal line test, we can see that a horizontal line crosses the graph at 2 points for y values between 0 and 2, as shown here. This means that the function has the same output, or y value, for 2 different input, or x values. Therefore, the function is not one-to-one. Let's look at f of negative 1 and f of 1, for example. For f of negative 1, we use the first piece because negative 1 is less than 0. Therefore, the function gives us negative 1 plus 2 equals 1. For f of 1, we use the second piece, x squared, because 1 is greater than or equal to 0. Therefore, the function gives us 1 squared equals 1. As we can see, two different x values, negative 1 and 1, produce the same y value, which is 1. In other words, the function has a repeated output. When we try to find the inverse, the input and output values are swapped. Therefore, the inverse would have 1 as an input that produces two different outputs, negative 1 and 1. This means that the inverse would not be a function. Therefore, we need to restrict the domain of the original function so that it becomes one-to-one. To do this, we need to remove the overlapping part of the ranges from one of the pieces. In this case, we can restrict the domain of the first piece from x less than 0 to x less than negative 2. This gives us the new piecewise function, f of x equals x plus 2 when x is less than negative 2, and f of x equals x squared when x is greater than or equal to 0. Here, we can check the graph of the restricted function with a horizontal line test to see it is indeed a one-to-one function, as illustrated here on our screen. Now that we have a one-to-one piecewise function, we can proceed to find its inverse. So let's see how we can do that. So to calculate the inverse of such function, we find the inverse piece by piece, meaning we treat each piece as a separate function. Let's see how we can do this together. First, let's invert the first piece, which is f of x equals x plus 2. We can rewrite it as y equals x plus 2 to make the process easier. Now we swap x and y, giving us x equals y plus 2. Then we solve for y by subtracting 2 from both sides, which gives us y equals x minus 2. Now here is the part that students often miss. What is the new domain? When we invert each piece, its domain also changes. To find the domain of an inverse piece, we need to find the range of the corresponding original piece. Remember, when we find an inverse, the original function's domain becomes the inverse's range, while the original function's range becomes the inverse's domain. For the first piece, the domain is x is less than negative 2. To determine its range, we evaluate the function at the boundary value, which is negative 2. So substituting negative 2 into f of x equals x plus 2 will give us f of negative 2 equals negative 2 plus 2, which results 0. Since the original domain is x is less than -2, the corresponding y values will be less than 0. Therefore, the range of this piece is y is less than 0. And remember, this range becomes the domain of the inverse. Therefore, the first piece of our inverse function will be f inverse of x equals x minus 2 whenever x is less than 0. This is the key idea to remember. When finding the inverse of a piecewise function, we invert not only the formula, but also the domain of each piece by using its original range. Now, for piece 2, we have f of x equals x squared for x is greater than or equal to 0. First, we write it as y equals x squared. After swapping x and y, we get x equals y squared. Solving for y, we get y equals plus or minus the square root of x. However, we only take the positive square root for this piece. Why? Because the original function is restricted to x is greater than or equal to 0, which means its outputs are also non-negative. In other words, the range of this piece is y is greater than or equal to 0. Therefore, we use y equals the square root of x. Now, let's determine the domain of the inverse, which is the range of the original piece. The original piece is f of x equals x squared with x is greater than or equal to 0. At the boundary value x equals 0, we get f of 0 equals 0 squared, which is equal to 0. And since x is greater than or equal to 0, the outputs of x squared are also y is greater than or equal to 0. Therefore, the range of the original piece is y is greater than or equal to 0, which becomes the domain of the inverse. Hence, our final inverse piecewise function will be f inverse of x equals to x minus 2 when x is less than 0, and f inverse of x equals to square root of x when x is greater than or equal to 0. And that's our inverse function. Notice that we didn't just invert the formulas. We also determined the new domain of each piece from the range of the original function. Here, we can graph the inverse function as shown. The first piece is f inverse of x equals x minus 2 for x less than 0. This is a linear function, and it approaches the point 0, -2. Since x equals 0 is not included in this piece, we use an open circle at 0, -2, and the graph is plotted as shown. The second piece is f inverse of x equals square root of x for x greater than or equal to 0, which starts at the point 0, 0 and is plotted as shown. Therefore, the graph of the inverse function looks like this. We can also use the vertical line test to check whether our inverse is indeed a function. As we can see, any vertical line intersects the graph at most once. Therefore, the inverse is indeed a function. Notice that the graph of the inverse function is actually the reflection of the original function across the line y equals x. We can also determine the domain and range of both the original function and its inverse. Since we defined the original function piece by piece, we can extract its domain directly from the intervals of the two pieces. The first piece has the domain -∞ to -2, and the second piece has the domain 0 to infinity. Therefore, the domain of the original function is -∞ to -2 union 0 to infinity. To determine the range of the original function, we can use the domain of its inverse, because the domain of the inverse is the range of the original function. From our inverse function, the domain is -∞ to 0 union 0 to infinity, which is simply all real numbers, or -∞ to infinity. For the inverse function, we simply interchange the domain and range of the original function. Therefore, the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original, as shown here. This should be fun. Let's try a harder example with 3 pieces: a linear piece, a quadratic piece, and a rational piece. Here, our function is defined as f of x equals to x minus 2 when x is less than 0, and f of x is x squared plus 3 when x is in the intervals 0 and 2, and finally f of x is 7 plus x minus 2 over x minus 1 when x is greater than or equal to 2. But as we have seen earlier, before we touch the algebra, we must first ask, is the original function 1-to-1? If the graph fails the horizontal line test, then the function does not have an inverse that is also a function. However, if it passes the horizontal line test, we can proceed to invert each piece separately. So let's graph our given function and see whether it is one-to-one or not. The graph of the linear expression will be as shown. The point 0, -2 is shown with an open circle because x equals 0 is not included in the domain of this piece. The second piece is the graph of the quadratic function, which is defined on the interval 0 is less than or equal to x, and x is less than 2. Therefore, the graph has a closed circle at x equals 0 and an open circle at x equals 2, as shown here. Finally, we have the rational function, which has a horizontal asymptote at y equals 8, as shown here. Now that we have the complete graph of our piecewise function, let's test it using the horizontal line test to determine whether the function is one-to-one. As we can see, any horizontal line intersects the graph at most once. Therefore, the function is one-to-one, which means we can proceed to find its inverse. Now let's find the inverse function. So let's start with the first piece, which is f of x equals x minus 2. When we find its inverse, we get f inverse of x equals to x plus 2. The original function is defined on the interval -infinity to 0. To determine the range of this piece, which will become the domain of its inverse, we evaluate the function at the boundary value x equals 0. So when we do, we get f of 0 equals 0 minus 2, which is equal to -2. Since the original domain is x less than 0, the corresponding range will be y less than -2. Therefore, the inverse piece, f inverse of x equals x plus 2, will be defined for x less than -2. Next, we have the quadratic piece, which is f of x equals x squared plus 3. When we evaluate its inverse, we get f inverse of x equals to square root of x minus 3, as shown here. To determine the domain of this inverse piece, we need to find the range of the original quadratic piece. The original piece is defined on the interval 0 less than or equal to x and x less than 2. When we substitute the lower boundary value, x equals 0, into the function, we get 0 squared plus 3, which is 3, so x must be greater than 3. And when we substitute the upper boundary value, x equals 2, we get 2 squared plus 3, which is 4 plus 3, which is equal to 7. Since x equals 0 is included, but x equals 2 is not included, the range of this piece will be 3 is less than or equal to y, and y is less than 7. And make sure x minus 3 is greater than or equal to 0, since negative numbers are not defined in square root function. Here, our lower boundary is 3, and square root of 3 minus 3 will be square root of 0. Therefore, the inverse piece will be f inverse of x equals square root of x minus 3, when 3 is less than or equal to x and x is less than 7. Finally, we have the rational piece. When we invert it, as shown here, we obtain f inverse of x equals 9 minus x over 8 minus x. Now, we need to determine its domain. The original rational piece starts at x equals 2. When we substitute x equals 2 into the original function, we get f of 2 equals 7. To find the other end of the range, we use a limit. As x approaches infinity, the rational term approaches 1. Therefore, the entire function approaches 7 plus 1 equals 8. However, it never actually reaches 8 because y equals 8 is the horizontal asymptote. Therefore, the range of the original rational piece will be 7 is less than or equal to y, and y is less than 8. This becomes the domain of the inverse. Therefore, f inverse of x will be 9 minus x over 8 minus x for the interval 7 is less than or equal to x and x is less than 8. Therefore, the function piece will be f inverse of x is defined as x plus 2 when x is less than -2, f inverse of x is equal to square root of x minus 3 when 3 is less than or equal to x and x is less than 7, and finally f inverse of x is equals to 9 minus x over 8 minus x when x is in the interval of 7 and 8, where 8 is in an open interval. Graphically, it will be plotted as shown here. Notice that the graph of the inverse is the reflection of the original function across the line y equals x. Also, notice an important property. The horizontal asymptote of the original function becomes a vertical asymptote in the inverse function. In this case, the original horizontal asymptote is y equals 8, so the inverse has the vertical asymptote x equals 8. All right, let's look at a practical example before we wrap up our lesson. Here, our question says that income tax in a certain country is calculated based on an individual's income level. If the income is less than or equal to $20,000, the income tax is calculated as 10% of the income. And if it is greater than $20,000, the income tax is calculated as $2,000 plus 20% of the amount above $20,000. So what we are required to find is the income level of an individual who pays $10,000 in income tax. To solve this question, first we need to form the income tax as a function of income by translating the word problem into mathematical expressions. Since we have two income categories, our function will be in piecewise form. For the first income category, the tax t is equal to 10% of the income I. Therefore, we can express it as t of I equals 0.1 times I when I is less than or equal to 20,000. And the second income category is defined as 2,000 plus 20% of the amount of income above $20,000. So it will be t of I equals to 2,000 plus 20% of I minus 20,000. This can be simplified as t of I equals to 2,000 plus 0.2i minus 4,000 when we distribute 20%, since 20% is 20 over 100, which is 0.2. Then we get 0.2i minus 2,000, since 2,000 minus 4,000 is minus 2,000. Therefore, our final function of tax, which is a function of income, so t of I, will be 0.1 times I when I is less than or equal to 20,000, and t of I is 0.2 times I minus 2,000 when I is greater than 20,000, as shown here on the screen. All right, now that we have our tax function, we need to find its inverse. The inverse will give us income as a function of tax, which is exactly what we need, because the question asks us to find the income level corresponding to a given tax amount. Now let's find the inverse of the first piece, which is t of I equals 0.1 times I. To do that, we just solve for I, meaning we multiply both sides by 10, and we get I equals 10 times t. Now, we need to determine the domain of this inverse piece. Remember, the domain of the inverse comes from the range of the original piece. The original piece is defined for I less than or equal to 20,000, so we check its value at the boundary value I equals 20,000. When I is 20,000, the tax will be t of 20,000 equals 0.1 times 20,000, which results 2,000. Therefore, the range of the first piece is t is less than or equal to 2,000, and this becomes the domain of the inverse. So the first piece of our inverse function is I of t equals 10t when t is less than or equal to 2,000. This means that for tax amounts up to $2,000, we can find the corresponding income simply by multiplying the tax amount by 10. The second piece is t of I equals to 0.2 times I minus 2,000. To find its inverse, we solve for I. When we do, we get 0.2 times I equals to t plus 2,000 by adding 2,000 to both sides. Then, when we multiply both sides by 5, we get I equals to 5 times t plus 10,000. And when we substitute 20,000 in the original function for evaluating the domain of the inverse, we get 0.2 times 20,000 minus 2,000, which is 4,000 minus 2,000, and this gives us 2,000. Since the original domain is I is greater than 20,000, the corresponding tax amounts are greater than $2,000. Therefore, the second inverse piece is defined for t is greater than $2,000. Hence, our complete inverse function is I of t will be 10 times t when t is less than or equal to 2,000, and 5 times t plus 10,000 when t is greater than 2,000. All right, now to solve for the required income level, we use the appropriate inverse piece equation. Since the tax paid is $10,000, we use the second piece because 10,000 is greater than 2,000. So we substitute t equals 10,000 in the piece function I of t equals to 5 times t plus 10,000. I of 10,000 will be 5 times 10,000 plus 10,000, which will be 50,000 plus 10,000, and this will result $60,000. Therefore, for an individual to pay $10,000 in income tax, their income must be $60,000. We can verify our answer by substituting t equals $60,000 into the original tax function. Since 60,000 is greater than 20,000, we use the second piece, which is t of I equals to 0.2 times income minus 2,000. Hence, t of 60,000 will be 0.2 times 60,000 minus 2,000, resulting 12,000 minus 2,000, which is 10,000. Therefore, our solution checks out. And we're almost done. You can always verify your answer by composing the functions, just as we discussed in our previous video. If you've done it correctly, f of f inverse of x should always simplify back to x for every x in the domain of the inverse. Since this video combines the concepts of piecewise functions and inverse functions, I'll put our previous video on these concepts in the description below. Before you go, watch out for these common pitfalls. First, inverting the formula but leaving the x interval the same. Remember, original range becomes inverse domain, so we need to determine the original function's range to find the inverse's domain. Second, forgetting to check if the function is one-to-one. If it's not, you might need to restrict the domain first, because a non-one-to-one function doesn't have an inverse function. Mastering piecewise inverses is all about keeping track of those intervals. Hopefully that makes sense and gives you a repeatable process you can use on your next test. If this walkthrough was helpful, go ahead and hit that subscribe button to keep practicing with us here at Rimetric Walkthrough. Thanks for watching, and I'll see you in the next video.